For undergrad students, again, if you feel that it's too much for you, just leave.
in peace.
In peace.
How very subtle that was.
I'm just gonna take this one again.
Daniel, you're not an undergrad, sorry.
He's going to leave right away, even before the beginning. And Dan, is he around? No, Dan didn't come.
He was complaining that
He was complaining that he didn't
no one
get
invites
notes.
I
You send it for sure, right?
I forgot to add
So
Spencer.
maybe we can send him again and send so where you are.
How do the rest of the PhD defense go?
How his defense?
Yeah.
He got it, yes.
Good.
Oh, you didn't see him after that?
Why? No,
So he
I haven't
disappeared
seen
right
him
away after the
since I
defense.
left. Yeah.
Okay, good afternoon, guys. And first of all, actually, I'm not well prepared for the presentation, and also those slides are not well connected, so please don't be offended on this one. And
Don't expect much.
so first of all, I tried to talk about some. I tried to show you some result what I got, and also this kind of preliminary result, and also talk about like what is the dephasing or what is the how hot areas to do. So a few points of what is the importance of this kind of thing, studying the nanomaterials for the hot carrier. So nanomaterials is advantageous because of their discrete energy state. So it should be helpful for give you the slower relaxation, so that you can get the more energy transfer to the part, which phenomenon is known as phonon bottleneck. But in some studies, most of the nanomaterials didn't show the phonon bottlenecks because of this. Rather than showing the higher probability of positive type processes, it means the hot carrier energy is transferred to the whole energy, whole state. And it also increases the Coulomb attractions because of the localized hole and electrons. So as such, it can increase the dephasing of the state. So you won't get enough time to energy transfer. Another thing is higher degree of thermal fluctuations because of it's not an ideal structure. So there are a huge surface compared to the core. So there will higher degree of surface reconstructions and also higher different types of phonon modes, so that it increases the probability of energy transfer. So those kind of positive. And next thing is we also talked about a lot of times dephasing and decoherence times. So I'm just showing what the dephasing actually is. In the first image showing, suppose like this one, with all of different waves, they have a phase difference and frequency difference. So it's all decoherence times. And in this case, they are also vector direction is the same, but they have a phase difference. And so it's also one kind of decoherence. In this case, all waves they have a phase similarity, but the direction is the way of the wave is different. So it's also decoherence state. So this is the coherence one. They're showing this coherence. So in a material, we want looking for more longer coherence state.
Is it allowed to stop in the middle?
Yes, it is.
Okay.
Yeah, it's kind of this. I'm not.
So can you tell a little bit more about this colorful figure in upper left? These 4 segments. There are no labels and it's not clear.
Yeah, this is just a random. I'm just showing there some random way to visualize what is actually coherence and decoherence. Is this a state?
But is there a name for each of the quadrants? Like the if you go to the out of this 4, if you go to lower right, everything is coherent, right?
Yeah, this one.
Yeah. Yes. What are the other 3? Do you have names for them?
What are the X's, by the way?
So in this first one, their phase and also their direction, everything is different. Frequency also different. Wave number is different.
So your X is what?
I mean, the propagation is axis.
X is time, Y is energy. X is time, Y is energy, right?
Y is not energy.
In this case, we go amplitude. Amplitude.
It is energy because the state's going up and down in energy.
It's amplitude.
Amplitude, yeah. There's amplitude.
But then the amplitude's shifted by a value.
But amplitude is not energy.
And you're given 3 other cases when there is a difference in phase, amplitude, and frequency.
Yeah. In this case, different frequency. In this case, frequency is the same, but their phase is different. In
Okay.
the fourth one. So third one. And the first one is everything is different. In the last one, the right lower bottom.
It's a great figure.
Sorry?
It's a great figure. You may add labels and
That would be
sell it
really
repeatedly again and again.
Yeah. So this is a very schematic difference of the different vector showing us. So this, if we able to keep this kind of coherence, you will get coherence is completely separated, isolated quantum system. But in nature, we know that these all systems are interactive systems. So due to that, is part of the system. So we will lose the coherence in the system. So if we get a longer coherence in the state, it will give you the more, and it can store the energy. So you will get a more time to transfer the energy to the. So this one is, I'm just showing another schematic figure. I'm saying to get from the OLEX paper. So it's showing because of
Which paper?
OLEX.
Oh, okay.
Paper, yeah. So due to the electron nuclear motion, so it's clear rather than getting this smooth potential surface, it's create a form for a little bit energy fluctuation in the surface. These introduce the decoherence in the system. And this is one of my energy.
Wait. If it is still allowed to stop?
Yeah.
Okay, so what's the difference on the left and right? For me, they look the same.
Okay, this one is showing that this energy fluctuation between these two states is very higher in this case. In this case, is very minimum or
So could you
equal. So here we can say that this is a coherent state. This is a higher decoherence.
Should you say that the concavity of the potential energy surfaces are not similar, therefore it leads to
concavity.
Is concavity, I guess.
Curvature?
curvature?
Concavity is too
Curvature
sophisticated.
difference is a fluctuation.
So if you approximate it as alpha x squared around the minima,
but
on the left side,
You talk about potential, right?
the potential, yes. Alpha 1 and alpha 2 are not similar, where on the right-hand side, they are similar.
Fine.
So
So he's
yeah,
talking about
it
the
depends. Yeah.
one parabola is much narrower than the parabola on the left. The top parabola on the left is much narrower than parabola in the
Which
bottom state. Right?
Different frequencies.
But that parabola also not a plane surface in this case because of electric motion. You get a
yes, obviously there is fluctuation, but in the overall scheme, if you smooth it to an easy to visualize function, x squared, then the bottom on the left side is much wider, where the top is much narrower.
Yeah, so you will get a phase difference of these two. So in that phase difference, actually, I guess, in that case, coherence time would be more longer than this scenario. If you take a smaller quantity.
Yeah, I'm just saying, other than just saying, look at the energy difference, you could say, look at the second derivative, the derivative of energy, and say, hey, we can get something that way as well.
That also, yeah, can be visible from this image. If this curve
Это будет
concavity is different, so that means they have a phase difference.
медленнее.
That will introduce the decoherence on that.
So when again, which of these cases would be having the so you talk about coherence or decoherence? I don't know. Which one is the largest decoherence?
This one is the first one is a more larger decoherence.
Larger decoherence.
Yeah.
Smaller coherence.
So yes, smaller coherence there. So So this one is showing how this energy is fluctuated due to the nuclear motions in the molecular dynamics.
For each system.
This one I'll just put as an example, so I get it from the quantum, so nanopairs for left solenoids.
So heavy atoms.
Heavy.
With low, with long period.
Then we also have a chlorine. Chlorine is a comparatively lighter. So this is the system what I showed the energy on the previous page here. So this is actually a 4-unit cell I'm showing this image. So this is making a nanoplex. So I'm going to talk about something also that before starting this I'm showing how the hot electrons and hot holes can relax in this one. So these two dynamics, the first one I excited the electrons to the 2.5 band gap energy and electron volt. And this one is three times of band gap energy. So it's showing that these electrons is relax pretty slow or hot electrons compared to the hot hole. And the hot hole relaxation time is pretty much the same, and relaxation rate is also same increase. I mean energy relaxation time in the 3 electron band gap excited. So to do that, now we need to look on what's the reason of this slower relaxation and why is faster relaxations and which phonon mode is coupled with this hot electrons and hot holes. So that's why we look for. So here's the overall picture I'm just showing.
So before we go to the next slide, did you look at the nanobatic coupling, like the magnitude for occupied and unoccupied? Because that could also lead to the very slow relaxation.
Yes, I haven't put on the slide presentation here. So that was showing the hot hole. Occupied state has a higher, almost 1.5 times bigger coupling constant compared to the unoccupied state.
And
so that's also increased the volume.
The occupied states are chlorine and
occupied state has a chlorine, but in the excitation state, in this range, this range has a chlorine contribution more than this one. But in this case, compared to the electrons, hole has a more contribution from the chlorine, but not significantly, because they have significant contribution coming from heavier like selenium atoms and also lead. So to do that, to state the phonon, this one is showing the dynamics image. This video is showing the vibration. So we had a very argument with the Levi about these equations, how to interpret these equations. So we wanted to look on the dephasing and also frequency. So before doing that, we can get a frequency from by the fast Fourier transformation. So that before doing that, we want to do the autocorrelation of the energy fluctuation. So in this case, I try to do this type of autocorrelations. And what I understand from these equations, this autocorrelation is this curly bracket, this is ensemble average, and Eij of t, so it's giving us the area of the time multiplied by the initial time energy difference. Is it? Am I right in this things?
Yeah, I guess you need to explain it better. Maybe, right?
No, I mean
on the whiteboard. So what's the difference between this? Well, first of all, what are these indexes in the energy?
Okay.
What is? I understand what is your Cij, but what is your Eij? Because energy should have just a single.
But it's delta Eij.
Right. That's exactly I wanted him to explain.
Oh.
So by now you just reproduced what is on the slide. Okay.
Sorry?
By now you just reproduced what is on the slide.
It's okay.
Yeah, I just type in the equation and then I can go through that one. Yeah. So yeah.
Because he can't really see what is in this. It's very bluish.
Okay.
Ei of t minus
J.
Well,
Yeah,
this is
it's
J.
two different indices. Oh, this is J.
Yeah,
Okay,
this is
whatever.
J minus
So it's vertical transition energy between two.
between the two state I and J state.
So here is just difference at the same moment of time,
Yeah.
right? Between each level, between
Mhm.
each maybe not neighboring, each pair of levels,
Yeah.
right? Okay.
And my interpretation
And
of
your
this number
your
is,
delta ij0, yeah.
yeah, this my interpretation is this is energy, the same energy when t equal to 0. Is it not?
Okay.
Okay.
And what?
So is
Which
that-
subject you have?
And then
So
how
I'm
you
looking at the
Discrepancy.
function. So this because I understand that because dephasing depends on your initial state. So all your trajectory, how it will do the dephase and all other things depends on your how you started initial observable state.
Can I write something and you will tell whether you whether it can be wrong, but just help me to interpret.
And I'm
what
also
you're doing.
wrong, yeah.
Oh. So anyone put equal sign between this or not? Please,
So he's kind of opening your averaging piece, right? So he already put this average as integral,
No, the
right?
So the only if I can be wrong, but what I see, it is important only energy offset between your 0 and t. But
So-
since you are using ergodicity, you are using different. You take very long trajectory, and you are offsetting from the starting point to have different representation of ensemble, and this would correspond to the tau. Right? Then this would be an average.
so this might be how I interpret this.
Oh,
is-
just a second. What Dmitry is saying that where's your so we have the timeline, right? So like we go this trajectory from 0 to I don't know how many you have, 5,000 or whatever your femtosecond, for example, right? Trajectory, and we reserve some initial piece from this one, saying that each point here will be considered as initial condition, as initial state. So let's say this one, now the actual trajectory would be whatever you have here minus this, let's call it tau as a maximum, minus this, right? So then this guy would be so 1, right? And then the last one will end up.
Yeah, that is how ensemble average we do for this spectrum. Right?
Yes. So I'm.
Yeah.
The
So
angular
this
brackets
tau-
were put there by Levi, not by me.
Tau stays
Yeah.
tau
So-
stays as kind of time, which is not really time in our case. It's just the number of the ensemble. Because you can think this is how the geometry changes with time, or you just say, well, each point along this trajectory would correspond some configuration, right? And then you can say, oh, this is my quantum dot having this specific geometry, and then it's moving with time. Now this is new quantum dot from ensemble, from the sample, experimental sample, right? And then it's moving along this trajectory. And this was another quantum dot moving now up to, for the same, in this case, 5,000 minus 500 femtosecond, right? But so time of motion is the same, of the dynamics is the same, but now each initial T0 is different, right? Or maybe, yeah, your T0 is tau, right? Yes.
So is this
So your tau is now represent this initial
initial time at that
T
time? Yeah.
equals 0 in your notation.
So is this the same thing
Ju-
as these equations?
Yeah, but in you writing your delta symbols, you probably skip the letter E capital, right?
Oh, yes.
It's okay, we understand.
We understand.
But
But
these
wait,
equations using the same
wait.
equations?
The summation uses index n that runs from equals 1 to n capital to
So this is
300.
my ensemble size.
Yes.
Yeah.
But your variables is delta E sub ij do not include index n.
Yeah.
How do they differ from each other?
So this is ensemble 300 different trajectories.
How do I know that your energy or delta in energy depends on n, on index?
He's
Oh,
he's
okay.
Put index n
confused.
somewhere.
He's confused because what you have inside your sum doesn't have
So-
any
oh, okay.
relationship to your
So-
indexes in the sum. No, it will not
No.
help.
So this is the
Yeah, I'm
energy
more
at that ensemble, at that number
Good.
trajectory.
okay.
And this is the initial energy of that trajectory.
Okay.
Is that
Now it is your general expression before you apply ergodicity hypothesis, right? If you have 300 independent ensembles.
So in other words, you can really make 300 different structures initially just by hand, or how many? 500 structures by hand, right? And then simultaneously run 500 jobs for the time 4,500 femtosecond, run it, then average and so on, right?
So yeah, my question is this equation is same or different? I mean,
They are
still
same
something
in
different.
idea, but they're different in a way that with this average we really take time instead of different configurations.
But wouldn't Dimitri's
Wait, just delta E I j of t plus n time step. After you apply your ergodicity in the practical way, how you do. Same as Svetlana was drawing. So your representation of an ensemble number n
Mhm.
is you extract it from the same ensemble without index, but you offset it
Yeah.
by
Initial,
some
initial,
shift.
So in
your
this
time
case,
now
we
is
take-
shifted by
yeah,
some number,
some
which
number
means
one.
your shift is corresponds to the ensemble number one, ensemble number piece of ensemble
So,
number 1, 2, 3, and
in
so
my
on.
first one, the first initial state will be the first state in the dynamics, but in the when n equal to 2, my first state is actually second state in the dynamics.
Yes.
So this is the average of the
So-
300 different independent trajectories.
So then,
In other words.
Ideally, yes, it should be 300 independent, but
but in our case, they're dependent.
Yeah, no,
so
okay, yeah.
Dimitri, if we did this now, this would be a single value, correct? When you integrate, you get one value.
No, you will be dependent on time, right?
It will
Because
be
you integrate
function.
over
function
the
of t.
tau.
You
See,
integrate.
you have
Oh,
two
oh, yeah,
variables,
yeah.
t and tau, and you integrate over tau, but you leave your t, so you will get the function on t, which
Right.
still depends on t, right? Integration doesn't go through t, only through tau. In other words, you sum over
Yeah.
ensemble, so you don't need to average angles here, right?
No, you still.
No,
need
you
it.
don't, because your integration is already covering this average of ensemble.
No, because that tau here would be this area here.
No,
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 look,
no.
No, tau is just
Offset from
Tau
from
goes-
origin.
tau is here, from
Then-
0
then-
to wherever your
Then
maximum.
this is not correct, in my opinion. How I read this formula, and this is where we were debating.
Please.
yeah we.
So, if we look at the papers that have this, they have a function that they have, it's kind of an enveloped by like linear.
We don't know what you're
Okay.
talking about, because I guess no one reads this paper.
So they have something that starts really high, and then it
What are you
kind of
drawing? What is it?
Autocorrelation function.
You're drawing
so
after correlation function,
Bij.
but it's already the result of this formula, right? You kind of get
Yeah,
into the final result
Yes,
of this formula.
they take this. and
Then
they
you
plot
get in
this.
something like that, okay?
Correct.
Is moving final result to equations.
Yeah, so I'm looking at what they did and interpreting what they got and interpreting how they got it. Because this,
But if you take Dimitri's integral, you also will get some function on t, which probably will oscillate in the same way as you draw it. How you can prove that this is not the same result?
so when you put yours, is tau if you do e of tau, that's a single value, correct?
E of tau.
Okay.
delta E of tau.
This.
Yeah, yeah.
There's a single value.
Okay.
And this is also a single value.
No, it
No,
depends
this
on
is a function
time.
of time.
It
No,
changes
it-
with time.
No,
If you fix your time, yes, it's a single value, but it's different when your time
You-
goes from wherever your
It's not
initial.
two values. You need to repeat this procedure
For
for
example,
functions
For in this
that
time-
depend on.
this t,
Tau is a
right?
constant term, right?
If you start in here, so your t equals kind of 0, right? Then 1, 2, 3, 4, and up to the 4,500, right? And your tau equals 0. Then you move on to the next one. Tau equals, I don't know, 10. Then your initial time also starts
but
at 10, and then it goes up to 400. I have a problem to calculate now.
So that,
600,
that's
4,600.
so
explicit
if
way of
you said
describing
tau equals
this
0,
curly bracket.
would
It's for the very first step.
Yes.
Wait. This is the value of your tau from 0 to whatever your maximum of number of which characterize the number of ensemble.
reading the papers, they say that if we do this is the sum of
Yes, yes. No contradiction.
but
It agrees well. You just plug in t equals 0
but they do it for the entire
for entire. Yes,
trajectory.
yes.
So that goes from 0. How Svetlana was saying it is it only looks at the initial point.
No,
Yes.
I didn't say it.
The tau goes
Wherever
for initial point.
Your initial tau is fixed. You take one value from 0 to tau. Your t goes from wherever your initial tau up to the end of the trajectory minus tau.
So in this formula, this all t started from here. So all t is a
You
different
go
number.
for all
But
t.
in this equation, you can use the same t, but that t is changing by tau.
You kind of shift it. It's exactly what I draw. Your tau is shift
It's something
in your
like
trajectory, in
this,
your time.
In this calculation, this all are 0 here, but in this one is a 0, 0 plus tau, 1, 0 plus. So it's actually 1, 2. Is it something like that?
I like how you explain it.
And again, we don't see contradictions between what you're writing in your squared guys versus both of these formulas. Like, I don't understand why you think it's wrong.
So this t, does it depend on which
T is
trajectory you're at?
T is a
Yeah.
variable.
No, I
What do you mean it
You
depends?
mean t or tau?
T is
Wait,
a
wait, wait.
variable. T is a variable
T
which
just a second.
changes
T-
with your time.
T is difference between initial point of given trajectory and value along the selected trajectory that we inspect right now. So
in this case, this t is universal. Then this t will change by tau. But
So
in this case, t
if-
is different.
If we say 0 here, then
it will be no average. Then tau equals 0 and it will
Means
be
you're not taking the average, right? You don't have ensemble.
It's just to follow only one. It's not changing. It's not moving.
so it will be
so
very
then if
If
we
you
put
want to
0
have-
here,
If you want to have the average, right, you need to have ensemble. You need your tau being more than 0.
so this t is that t.
yes.
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 So this is 0, that's 0, that dies. Okay, then it's a square.
hmm So then it's in a good agreement with your formula, which
So
you know.
in that case, it shouldn't be bracket here.
Yeah, we don't need
Yeah.
brackets. It's already in this integration.
I do not need
This
brackets.
is here.
Levi may need.
Okay.
Yeah. So
Yeah.
integrate. Well, think about average means what? Sum over divided by how many of them, right? which you can rewrite in a more fancy way through the integral if you have very small, if your sum is not really discrete, right? If you have very small splitting between each value in the sum. Yeah,
Tau max, yes. And then in the denominator,
it's
Oh.
tau.
It should be the same. Yeah, keep tau.
Tau on a maximum.
Tau max, and
one
then
over
in front.
In front, it's 1
factor in
over tau,
Yes,
not
yes,
t, right?
yes.
And I think it's tau.
Yes. Excellent. Thank you. Excellent.
Are we good? Actually, I forgot. What was the question in the very beginning?
So
What is it?
This is kind of my interpretation of this equation.
So then,
So Levi has a different interpretation of
do
this
we
one here.
vary tau
Yes, we do.
max? So
No,
we say
max-
tau,
no,
tau max
tau
is
max is
0.
fine.
Just your tau is just the number of ensemble, the size of your ensemble.
Ensemble, yeah.
So let's say you have 300 structures.
So in this tau max equal to 300 in our calculations. So we need to go one. You need to.
And
take it 300.
UT is kind of variable which is defined in a window from 0 to 1000,
Just
right?
to
So,
make
but because you take in 300
then-
reserve,
Levi,
it just goes
just
from
for your comfort,
0 to 700.
consider as it would be comma, a function of two variables.
Nah.
Do not do it in public. Just
Because this
For
is
thinking.
more confusing.
Okay.
no.
No,
So
I-
we do
if
this.
you
This
put
is more
commas, then
confusing.
it's unclear how they relate.
how
But
they
here
relate.
it's just a constant which
So-
shift your t by some values. That's it.
that t to get this, then we put in 0, 1 to the number of time steps, correct?
We screen different values of t.
Like this t, this initial
That-
zero, right,
that-
is different because
Yes.
this delta g depends
Yeah.
for your
So
ensemble, and of
tau
course
tells
it
you your
dictates
initial
different e
positioning,
because
right?
this
And then
t
t
Yeah,
is
is
like
dictated by
how
this
Yes.
integral, right? So in
Yeah.
one case it's
Yeah.
this, in the
What
other
key is
case
that
it's that, in the
yes,
other case it's that.
but this
For every
this
case.
should output a function.
It is
Thi-
function.
This one is a function. This one will give you a function, and this is a
So-
one
And this is a
number.
constant.
Next time, Levi needs to present what is ergodic hypothesis from statistical mechanics.
Great. See? So next Friday you present on ergodic theorem and what does it mean?
Okay. It's gonna
Ergodic
be-
theorem and how is it implied
So
in the
this
statistics?
should give us an array.
It gives you a function. Well, why is it an array?
Okay, we have discrete values.
Okay, you have a discrete
Okay.
values. Well, it's actually your Cij depending on t, right? So you will have different values at different moments of time. It's a function on time.
Sure.
Good?
I think so.
Okay. Which will do some oscillations, kind of dying out at the end of your t. The further you go with t, the less oscillations your correlation function should show.
This group meeting looks like what Kieran Burke was explaining about Walter Korn.
34.
Walter
What
Korn.
is the
Just
Hamiltonian?
write Hamiltonian
And then you have a discussion for 2 hours. Everyone with us, I'm not sure that everyone, but are you against us? Are you happy with?
Anyone against ergodic hypothesis?
No one wants to add any symbols to the equations, any corrections? No? You good as it is?
So
Perfect.
So that equation, what you can talk about so far, this is autocorrelation function that just correlate with the initial state with the space, and then second one is just normalizing with this the terms. And then if you want to know the phonon mode, which is coupled with that state, so we can do the fast Fourier transform of that.
And before you go, so your denominator, your normalization constant, it's exactly what Levi showing
that initial
here,
one,
right?
yeah.
So you kind of assume that it's equal.
Yeah, that should be this term, the square of this.
Jabba? In the last equation, the last line on the right part, should it be C of t? It doesn't make
Inside the integral or where?
Yes.
Yeah, because you
It
integrate
doesn't
over
make sense to
t.
integrate over time a function
there
that
is
depends
no-
on frequency only. Should be a typo.
Yeah, it's typo there. Because we are getting the wave number.
You want to
after
get the result.
After the fast Fourier transform.
You want to have a result which will have dependence on frequency, right? Only. But your initial, what you have inside the integral, depends on t.
Yeah.
Can I ask like
This is just the image I took from paper, so I didn't look on the exact.
Also, they had a typo there.
offside
Yeah.
question. Through the code that you already operate, will you be able to do the same procedure, putting instead of delta Eij the non-adiabatic couplings V sub ij, and find their autocorrelation function? Should you be able? Technically.
Yes.
Energy changing.
So you're saying instead of
Energy
energy,
to
you
there.
want to see the
Instead-
couplings.
Like energy delta
But the
Eg.
problem is we have couplings.
No, you have all couplings for all pairs of
The
orbitals.
dimensionality of couplings is larger than difference
The
in energy,
coupling
right?
of that state with the I think.
Hmm?
Coupling of that state with the for next state,
Mhm.
not all.
Not
Mhm.
all. Okay,
Not
so
all,
just
yeah.
nearest ones, right?
Mhm.
Nearest, yeah.
Okay, yeah, then we can, because otherwise you have
Okay.
all of them.
Yep.
I need to look on that. I'm not sure.
What physical means then you expect?
Presence of memory. They should decay much quicker than energy autocorrelation.
Oh,
So that's
Mhm.
not really
But-
fluid.
for energy, we already see that they decohere in like 5 femtoseconds.
For off-diagonal element, they will decohere in 1 femtosecond.
Which we can't resolve. We can't. Currently, it is a practicality.
It's
of,
good. It is so good. They disappear quickly. It's a good proof. Yes.
So this is the image I'm showing out of the box from the last equation and previous equations. So in the first panel, what I did, I just take the energy difference of the initial excited state for four occupied and unoccupied state. So that means hot hole and hot electrons. So this frequency is showing that.
Before you go there. So in your equations, you were taking difference between I and j values, right?
Yeah.
When you create your correlation function. So here you say HOMA and LUMA, then you're using this approach or you use something different?
For the hot electrons and hot hole, I use following this.
Then what is your I and j?
In this case, I is I separated what we call decouple hot electrons and holes. So it is the electron energy and hot hole energy. So that means
No.
I and J. I is HOMO in case of
But there are
hole.
two indexes, there are two energy levels, right? So
Yeah.
then which one?
Yeah, I is HOMO and J is excited. That whole state.
The initial excited state.
Yeah. And in case of electrons, I is LUMO and J is initial excited.
But
So-
then on the bottom you just have HOMA and LUMA, then what
At
is
the
this?
bottom, I just take the electron hole and HOMO energy.
so you do a fast Fourier of just the
Yeah,
energy.
The level.
Yeah.
So not delta, but just
delta.
like instead of delta,
So
you
you
will
learn
have
how
just
to-
EI minus. I mean EI delta EI 0.
Yeah, so there are no
That's it.
autocorrelations in this case, so it's just fast Fourier of the energy.
Okay.
So in this case, in the electrons and hole, it's showing that they are coupled with the different electron modes, and maybe so that also gives us a reason why electrons and hole is relax at different rates, because maybe hole is coupled with some phonon modes, which is what they call accelerated acceleration rate. And in case of frontal orbital, HOMO and LUMO, so they are coupled with a very similar phonon modes. And if we look, if we compare with the hot electron, they are also different ones. And to look on this one, this phonon mode, this phonon mode is coming from which type of vibrations, we didn't able to calculate the normal mode. So that's what we did. I just take the molecular dynamics trajectory and then calculate the vibrations of the specific bands, specific bond, left to right and left selenium bond. In my system, they have no selenium bond. So what I did here in this case, I first take a bond pair from the initial state and then calculate all of this pair individually through the trajectory, and then take the first Fourier transform of that energy, and then this average is the n here is the number of that specific type of bonds, and then I take the average and then showing this from here. So in this case, the left to right has a very high energy.
But you also need to have then lead and selenium as well, right? Because again, it's not just bond; it's some kind of vibrations, which you also can think about the change in the distance between two lead. Also, of course, will contribute to some normal mode.
That vibrations only coupled with the nearest to bonded atoms only.
No.
Your lead also might be nearest one. They're not very far away.
When I did it for the core shell, the metal interaction showed a lot of spectral density.
And you can see, like, if you look on your motion, like this movie which you have shown, right? So you clearly see that you sometimes, the bond distance decreasing, so you're really creating a bond between two leads or between two seleniums, and then they kind of going apart. So like these vibrations, you can also think that, of course, they exist, right? We don't call them a bond, lead or selenium bond, right? But they kind of coexist.
So that in this case, I consider the diameter as a covalent bond diameter of the atoms. So previously, I calculated with the van der Waals diameter of every type of
I thought you just take the difference between coordinates of each atom.
No, I mean how I define the bond. So if the distance between these two atoms is less than 1.5 times of covalent diameter of that bond, so then I consider that as a bond.
Why don't you just?
Well, I don't can. Then again, you. This is not then how to say. You're really selecting some specific vibrations, right? You're not showing the phonon spectra. It's again, you just specifically showing this specific type of vibrational motion, and there might be much more normal modes there, which you not even include, right? So you kind of, I would say, you over-specify the type of vibrational motion in this way. And honestly, I don't think you really need to worry about the bond radius or anything about like what kind of information it gives.
Then it would be numerically a lot of different, huge number of.
But you run it once and you're done forever.
Yeah, that's. So now,
because you take the difference and average it, right?
No.
How you do it?
So when I did it, I did the FFT for each pair. So get
lead, selenium,
each
fluorine.
pair of atoms I looked at, I did the FFT over the entire trajectory. So if you have 100 atoms,
and you take the average of them, right?
then it's like 100 factorial over 2 factorial times 98 factorial, something like that.
Okay, good.
So it has a ton that you have to do. So I think when I did it, I excluded some of them because I was like, I don't want to take all the time, but it doesn't really take that long. It might go from 3 minutes to 20 minutes.
So you're taking nearest neighbors, all nearest atoms.
I'm doing something similar.
But you take the all
and you
take the average at that time instead, right?
No, I do the FFT on the raw data, and then I average the frequency, like the amplitude at each frequency.
So in this case, what I did, I just take a bond pair from the initial time, I assign that bond, I look on that bond, that two specific atoms throughout the trajectory.
From your formula, you did exactly what I did.
So
in average FFT omega.
But he defines his Rij.
I define Rij.
Rij, isn't that the distance between?
Yeah.
In time?
But his.
No, I took it from the initial state. I defined the bond. Suppose I have one chlorine and lead bond, and
But what if
I
they?
check that
What if they
distance.
at some moment of time? What if they far away from? Because vibrations. What? The bond is not applicable when you talk about vibrations. It vibrates around equilibrium means
Yeah.
it becomes longer than the bond
Yeah,
radius.
yeah, I
Or
put
smaller, right?
yeah.
So shorter, longer, shorter, longer. In average, you will have your how you call it, van der Waals or whatever your radius you were
Yeah.
using for the bonds, right?
Yeah, I defined that initial time. Then I didn't put that condition.
But
throughout
in
the
your
time.
formula,
No.
Rij with T.
So yeah, that's why I just put separately here. So I defined that pair at initial time by putting these conditions, like what the distance between them, and then I take that distance, calculate that distance between that pair of atoms throughout the time.
Oh, okay. And then you're not really worry about the like you just say
Kind of initial.
you number like wherever the atoms are in this condition
Mm.
at the moment time, then you consider all like they all considered during the dynamic.
Yeah,
Doesn't
yeah.
matter whether the radius is changing or not.
Yeah, only I exclude few trajectory, which is like some atoms is
So you use this just to define your nearest neighbors.
initial time.
Mhm.
Define the pair of atoms.
So,
where,
Are you
close to each
taking the raw data that might oscillate around like
What is-
3?
With
like,
raw means like
you run the dynamics, you compute the distance between atom I and J, and you have oscillation at the at like let's say 3 angstroms, right?
Mhm.
So it oscillates around 3. So what is this? What you're saying? Find the initial value, and then take the oscillation minus that. So if it's around oscillates around 3, do you scale it to 0, and then it oscillates around 0?
I don't get you. Okay, let me explain this. I guess it will help you. In this case, this is the FFT of a pair of atoms. It's a chlorine, lead, or this one. And that pair, which pair? I didn't take the all pairs. I just take the pairs which at initial time where the distance is equal or less than this number.
Yeah. So you're
Then
just
I level that two atoms and then take the distance of the change of the distance over time and then to take the 50.
so
Make sense?
In this case, I would say you probably need to figure out these atoms not on initial time, but at 0 Kelvin.
So
No.
Like just to figure out which really create these bonds, right? Because in additional time, some of them might be already being
Yeah, that's
out
very
because you equilibrate your
very much
system, right?
arbitrary, yeah.
Some of them might be already out of this bond,
Mhm.
but then since they oscillate, they might come back to it, right?
Mhm.
So I would say then you need to apply this in your 0 Kelvin structure, right? Then you
Mhm.
have list of atoms contributing to these bonds, and then run your and then based on these indexes of atoms, you run it on a
what
dynamics.
I remember, I did one time for trial calculations. One time I did like take this leveling not from t equal to 0, just randomly middle trajectory, and then take this
But again, phonons, it's a collective motion of all atoms, not only neighboring ones, right? And they might be more than 2 actually contributes to the same to the same kind of vibration. So that's why kind of you might see that your lead and selenium kind of change in their position really might be appearing in a range of
Maybe,
these big
yeah.
peaks rather than lead selenium and lead chlorine.
Maybe it will miss the transverse optical mode, so it will only give us the electron.
Yeah, so I mean, you can apply this, but then we redefine your radius for lead, selenium, because of course they're bigger than.
Yeah, maybe that's why we did not get anything higher than 200 in this lead chloride.
So I don't remember I forgot in your you were
Like it was
using
like 250, like
for
230.
for lead selenium or lead sulfide, I don't remember, right? Or for
I think
selenium.
it's cadmium was higher in energy.
Uh-huh.
So I think that's about right for what I had. Actually, it's shifted, but it's different systems. So going back, do you do the black line, the FFT, or do you do the dashed line? So it's hard to draw. The only thing different between the black line and dashed line is like you take
What is the
that
dash line? Oh, I see. Along the
along zero. So you take like the average over the time, and you subtract the average from.
So what is this Ri z equal to 0 means?
That means that's when it's at the average length, or at time 0.
No, I did not take any average length. I just take
Okay,
the
so
line.
you just took the raw
Yeah.
FFT.
Oh.
And in your spectra, you averaged kind of, right?
I took
So-
away, I believe, and made it oscillate around 0 because when we do this, I remember the autocorrelation of energy. Somewhere
So that's why
Oleg
in
said
this case,
shift it to
yeah.
0 because otherwise if you have a state that oscillates around 5 eV difference versus 2 eV difference, that could implement, that could change the data. So that's why I asked, because I only remembered that after this.
So that's why in this case, suppose like black line is average of like about 45, 50 because we have only 24 silver chlorine atoms. So, but other one, that selenite is more than 350 here, different ones. So, okay, so this is kind of giving us some idea about what type of phonon modes is coming from this type of atom. So since I considered only 2 atoms per pair, 1 atom pair, so I hope they have no transverse optical mobility included in here. So that's like close to the 200. So let's pick the next picture. I'm just showing what is the average of this one. So
It's cool picture, but kind of completely unclear.
Competitive for cover art.
Yeah.
As I told you, I take the like a lot of FFT, and then because my trajectory number is average
Ensemble.
size is 300 ensemble size, as we discussed about the equations, the tau and my Tmax is 300. So what I showed in this case, this is the average of the 300 different FFT. So if you look at this picture, there are some very unexpected density, some frequencies very high, some are comparatively lower density. So, but if you look individual one, this also has a significant contribution. This red line is saying of this wave number, but number of that kind of trajectory is lower compared to other one. That's why it's minimizes spectral density. So why I'm showing this one is saying that I'm just trying to say, although if there's some peaks are lower density, but those still
And
very-
again, what's the difference between right and left panels?
So this is for whole electrons, this for hole.
Okay.
Left is
But then we have no any contribution after 200, right? In both, well, a little bit on a whole, but
yeah, that's what I'm
but
saying.
your picture showing something there, right?
Yeah, in this one they have a very low spectral density. So in picture, it's showing the sum of half or sum doesn't have. So therefore, when I take the average, minimize this which is diminish this feature.
And experimentally, which frequencies are typical for this material?
Optical frequency is around 200 and 250.
Most of the time, I guess you have about around 200 optical frequency for left to right.
Okay.
And it's also very hard to compare with this one with the bulk or other materials. Okay, so this is about the dephasing. Next part is about the dephasing. I don't have much result about dephasing. I just put the two equations how they calculate this paper. In the previous discussion, we talked about the autocorrelation function, the Cizer, then we can use that Cizer to calculate the dephasing function. Dephasing function will give you that of the time how fast it will lose the coherency. And I calculate this for using
Javed,
yeah.
can I keep interrupting? So what is omega? And where it comes from? Yes.
Omega equivalent, if I remember, can calculate the omega from the energy difference in the time. So divide by time or time step? Gravity, I guess. Or maybe not this one. I forgot this one.
By dimensionality, it should be Planck's constant.
This one.
So you're saying it's just frequency. You're trying to write it as a frequency.
H bar, yeah.
Frequency, right? It's just frequency. Well, angular
This one
frequency.
here, yeah.
And in your integration, you have energy. Inside the integral, you have delta E, and here you have frequency. So if you compare the units, I think one exponent is having the units of frequency, and another exponent having the units of frequency, because you already divided by each bar. Okay.
Yeah,
So
Yeah, then it's fine.
they should like compensate by accumulating phase
Okay.
in the opposite direction.
So you already put it in a frequency as well. Okay, good. Okay.
And this d of t should be real, or it comes out.
D of t
Yeah, it
of
should
tau.
be real,
D of
because
tau.
both have imaginary part in this both.
So they imaginary parts compensate each other. Is it like good wish, or it is you checked it?
I tried to.
Or you just
I
plot
tried to
you
program
you
this
plot
one, but
real
I had
part
a hard
without.
time.
This one is real, right? You cannot get imaginary.
Yeah, but
delta
it
E.
is exponential to this power.
So it's still real.
Exponential to the imaginary power.
No. Yes, but it. Okay. This part would be imaginary, but this one again, this is real. This is imaginary. So you have two imaginary as a product. So you will get real number. No way to get something different.
Only if the frequencies will be the same. So it could have imaginary part.
For
For d of t, yes.
Yeah. But it's supposed to be real in this whole case.
Okay.
So it's supposed because isn't it? Or am
I don't know. I'm just curious.
I tried to plot these equations, but I had
On the
a hard
real,
time.
you plot on the real part, right?
I do it like conjugate of this one here.
But
No,
you-
absolute number of this
You
one.
will have
Okay.
either real or either imaginary. You will not have real and imaginary at the same.
It will be like complex, oscillating, and having both real and imaginary.
Смотри, вот это real. Ты умножаешь на imaginary, а на самом деле полностью imaginary.
Мгм.
Как нет? Ты же просто умножаешь.
Okay,
But my code didn't work. I got a
okay.
lot
Let's
of
hope that
wrong.
it is real.
Yeah. I take absolute number of this, what I got, D, and then it's given just a 1 out of them. And I have another confusion about this actually curly bracket. Why would it can compare this T and inside the T? Because if we know this is ensemble average, but this part is outside this ensemble average. So, and I did not able to.
So what you computed the pure dephasing function.
Okay.
That
But
was
it
a
didn't-
question. That was not a statement.
Sorry.
Which formula you were using? The
Yeah,
top or
so-
the bottom one?
Yeah, in this case, I use a second order accumulator one. I tried to this one, but it didn't work. It gave us like 1 of the cases. Yeah. So by using this one, if you look my porting is
So you're
2.
saying that if you use the first formula, you get in what? You were not able to use it?
I'm not sure that my scripting is worked or is my fault or equation I somehow it didn't work. That's what I'm saying.
My fault equation.
Equation is guilty.
Because I did not understand about the curly bracket here because how can I put this T with the inside the ensemble of
You
this
just
T?
compute it for each trajectory, and you take the average over the time,
But what about this outside exponential?
and then you just times by the outside exponential.
But when I take the 300 different trajectory, that trajectory is not same as just one twist trajectory. You use this.
You compute the bracket, what's inside the bracket for each trajectory.
And then we got
You
only
average
one.
them.
Okay.
You get a single like single expression,
Trajectory.
Okay.
and then you times it by I omega t.
Oh, okay. So that means this t and this t is not necessarily same t.
Yeah, you will get something.
No,
This
they are the
just a
same.
second.
This t is
After
separate.
integration, the thing after integration. Look, you have a function which depends on tau and you integrate over tau. Means you losing your tau. It's not the variable anymore. It's a constant after integration, right? Because you whatever your expression after integration, you put these values, right? Kind of end up with some number. Well, in this case, it's not really number. It's t minus your maximum goes into the t, right? So you end up with this guy being whatever your expression having now t instead of tau. Right? Because of this limit. And in this case, I guess this t is really pretty much the same as that t. So they will have the same t. Oh,
It's the same
so
thing
think
that we
your
did
t is a
here.
number, right? So then this integration will give you just the number. But because it's not number, whatever you're getting after integration, right? You just instead of number put in t, so it would be now function on t.
Okay.
But not function, how to say, expression on t, I would say. It's not really function. It's something like, I don't know, maybe t square or something, whatever you get after doing this thing, right? And then this guy will be just multiplied, so you can take t as a common factor and then see what happens with this I omega comparing to the rest, which you have another omega after this integral, right? And this is what we just said, that if you have both omegas the same, that you have real, but if omegas here, because your delta E divided by H is like another omega. If this omega and that omega are not the same, right, then you will have the imaginary part for your dephasing.
But in the if I define the omega E del EI over H part, then it should be same omega here?
No, they might be
this,
different.
This integration part is given over del E, function of del E, and then over HR.
Well, again, this delta E not necessarily will end up with this omega.
In average, it can be close to it.
I think in the papers they say omega is equal to the average energy fluctuation.
Yeah, so after integration, you will get something very close then. And then the difference would be very similar
So
to the same.
as t goes to infinity,
okay. So
the integration will give omega, and
Mhm.
the overall thing will be
Constant.
yes,
Oh, real
yes,
number.
yes, better, yes.
I think, yeah, something like that.
But I don't understand. So, like, how many points? Like, why you're in a previous papers from Oleg's group, right? So they have definitely much smoother curve, and then they just feed it with Gaussian or something, right? In your case, you have 1, 2, 3
I didn't
points.
feed on Gaussian, I just plotted what
I understand. But my question is, why you have only 3 points? Like in Oleg's papers, they had many points for this curve, and you
So-
have only 3. How is it happening?
So,
Why you have such a
Oleg-
limited number of data points on your figure after doing
This
it?
paper uses time steps of 1 femto per second.
Why we cannot do
No,
it?
Well,
but
we
it's still,
can.
but it's still dephasing time.
Because
is
you
showing
go
the
in a much
considerably
shorter
longer
life.
dephasing time.
Yeah, so they use 1 femto per second. For the core shell project, we use 5.
No, but you use 5 going for trajectory up to how many? 5,000.
Yeah,
But
it's
for
about-
dephasing, your
even
window for
second
time
level
can be much smaller, right?
Yes.
So you go probably only 100 femtosecond.
I'm not saying that
And then we
can't-
can really reduce the step and make it.
No, this one
Much more
is
visible.
longer, but all number are zero, so it's getting the zero very fast. That's why.
I'm not asking about 0. I'm asking you have point number 1, point number 2, point number 3. What about points in between?
Because my podium is 2, so I can get only point every 2 femtoseconds.
So you need to recompute the whole trajectory in order to make.
But what's the problem to decrease your port team and run the trajectory, not to 5,000, but only for 100 femtosecond.
But then I need to start from the beginning. Do you think I need to recalculate?
But it's only 100 femtosecond.
But it's still not the same.
It's 1,000
data.
times less than what you already have. Oh, how many? 100 times less than what you've done.
But it won't be the same trajectory as we are calculating.
But
here.
you average them, doesn't matter.
But the initial geometries, if you have 1 femtosecond protein, your initial trajectories for each
Well,
your
technically, you
initial
even don't need
geometries-
100. It looks like it's dying out after 10. So, so you need to take your 300 ensembles.
No, but still we need the sufficient longer trajectory to get the correct frequency of that one. Then it will give us this operation.
Why couldn't you have like one run for each, right? You have your longer run with longer time steps, and then you have your shorter run just to get this number with short time steps.
But this number is got from the longer trajectory run.
So
But we need the sufficient longer trajectory to get the reliable data on this one.
For averaging, okay.
Yeah.
But you may have developed a plan for like your next project to start right away with like 0.1 of the femtosecond, and for a smaller system just for a test.
The problem is when we started with this project, I didn't have any idea about how we started from 5 femtosecond, but it didn't work. Then it started from 2 femtosecond. Now, because we already come so far, then we cannot start from the beginning again. But it will be give us a better. We should get a better result in the smaller.
So how long does it take to repeat all calculations, just for curiosity?
From the
beginning.
But again, we don't need 5,000 for this, right?
Just for curiosity, how long the
continuously,
yeah.
It don't take that time how long we right now because I learn and
Yes,
but now I know everything.
pure machine time. If you doing everything instantly, is it like 2 months or half a year?
So I
Maybe
recomputed
less than half a month.
all
Actually,
the stuff with Patrick's
obviously
paper with I
maybe
think
2 months.
2 femtosecond time steps.
But it looks like 2 femtosecond doesn't. Still, we don't. This is 2 femtosecond,
Yeah.
right?
For mine,
So we still
the
have just a
phasing
few
was
points there.
Up to like 10, because I had like 3 points. So mine is a bit longer. But that took about a week and a half to like.
So you can take months calculations, recalculate it with femtosecond or even. Are they using what they use for their calculations? Less than femtosecond?
1 or 1.5.
Okay, so 1 femtosecond. They're not using less than 1 femtosecond.
But it's still, is it like dephasing time is considerably very small, shorter in this case?
But the problem is you don't have reliable data to fit a Gaussian, it.
Yeah,
right?
but if you consider this, I mean, what's it called? Why cannot consider the middle of the Gaussian bell curve? Maybe around 2, or in
But-
maximum 4.
No,
But
you can
have
fit it.
like
It looks
4
pretty
data
Gaussian for me,
points.
no? Look, you probably can fit it with Gaussian.
Yeah,
You can.
Maximum and then
But
the
each of
dynamic.
the lifetime will be make less than 4 maximum, right?
Yes, but
Yeah.
what's
So-
your error on it?
No, I'm saying we can consider the maximum possible time here to qualitatively compare
Okay.
our results.
Anyway, nothing to argue right now, right? So because for sure we have 3 points. It's definitely not enough to plot anything except if it's a line, right?
Yeah.
You definitely can plot a line over 3 points, but if it's more complicated function, 3 points definitely not enough to predict the behavior. And it's supposed to be kind of Gaussian for fitting.
Yeah, that was I faced the problem when Dimitri asked me to work something on silver because we have only 2 points. That's why I didn't plot anything.
So which again means that you just need to rerun it for shorter trajectory. Maybe we don't need to average over 300. You can average over 100, sampling over 100, right? And shorter trajectory and small step. Several weeks you will get all this data. And it's like it's not necessarily, you don't need this to be exactly on the same set data which you were doing for the dynamics calculations, right? Because they kind of work for different purpose. So just new set of calculations with smaller step, shorter trajectory, maybe less averaging, don't need 300, go 200, 100 maybe. So you don't want to go less than 100, right? 100, at least 100, and trajectory 500 femtosecond. So 600, the whole trajectory is 600 femtosecond. With 1 femtosecond step, actually probably ends up with even quicker than 5,000 with, well, pretty much the same with 5 femtosecond or 2 picosecond, 2 femtosecond range steps, right?
Okay.
Yeah, and as soon as, let's say, Ben knows how to run BAS, you can ask him to run these calculations instead of
We are
you.
still working on Gaussian here, yeah. Okay, so in the last one, I guess it's the last slide. So this slide I'm showing the localizations of my.
Looks like slice of watermelon.
See, Joe, but I'm not the only one that said that.
You also talk about watermelon.
Yeah, that name also watermelon
Panel.
color palette. Okay. So what I'm showing here is the localization of hot hole and electrons over time. And in this calculation, what I did, I just calculated. I had a projected cost for each element, and then I have a hot electrons number and other one. Then I projected to z direction, because z direction is important because my nanoplate is a what's it called, periodicity has in the 2 directions, x and y directions. So this is thickness control, and I projected to the z-axis here.
So you integrate over x and y, right?
I integrate over x and y.
What is the difference between top row and lower row?
Yeah, and then top row is hot electrons, that means. And this one is the hot, sorry.
Top is electrons and bottom is hole.
No, top is hole and bottom one is electrons.
Ah, backward, okay.
Yeah.
And your time goes from
0 to 2
2.2
picosecond.
from bottom to the top,
bottom to the
like for field theory physicists.
top. A good compliment for you watching on film.
Yeah, but maybe we need more interpretation. What exactly
So then,
you mean by this
in a whole state, it's showing the initial time is delocalized before.
So, okay, if I look on your z equals 0. Show me on this 3-dimensional image. Z equals 0
Okay.
is bottom surface, right?
Okay,
Kind of.
this number I just copied directly from my script. So this is just a retainer. I divided I have a 6 layers, so I divided my cell in 12 different units. So they have no units. Don't consider this just.
So it's not nanometers.
No nanometer, nothing.
Oh,
It's just
angstroms maybe. I thought it's maybe angstroms. What's the size of your plate?
Yeah, that's
Z is what? 2 nanometer actually,
my
right?
plate size is 2 nanometers, and this one is one thing is 40 nanometers. Sorry, 4 nanometers, 40 angstrom. So they have a 10 angstrom vacuum is the sun. So this is the vacuum, and this is my nanoplate.
So your nanoplate goes from 2 to 9.
Yeah, this number is just arbitrary.
Yeah, but I mean, according to your numbers, what you really have atoms is from 2 to 9, roughly speaking, right?
And these are empty vacuum, this because I have a previous one. So that's why it's up to here. And this area means this surface area we can consider, and this what is hole. So in the hole, this mainly coming delocalized over everything in either case, or is going to localize from the surface state over time. So we know that if in the DOS, this mainly is selenium is more contributions, and unoccupied is mainly contribution from lab. So this is this number. We have in these cases, this is mainly from lab, and this is mainly from selenium. So initially, if you look at here in the fluorine cases, is localized on the surface and then is transferred to the silicon, but also selenium is still on the surface edge. But in case of fluorine, electrons, if it's delocalizing everywhere, but with the time is mainly going to the core of this nanoplate. So that means the core state is more susceptible from the surface deconstruction, and also it's coupled with the surface phonon. so that which increase the relaxation rate for the whole state. But in the core, it's more safe in this case because in electrons it is localized on the central part. So central part and most of the chlorine also on the surface, and central part core is mainly from selenium and lead, which is heavy atoms. And so it's kind of gives us a slow relaxation rate. So this is given some like idea about localization of the electron and hole state. So this is not a conclusion, just few observations what I found, what I talked about, like about the phonons and the chlorine contributions of that one, and how electron doesn't couple with the surface phonons due to the localization on the 4 nanoparticle slope, and which decreases the relaxation time. And that's all about today.
Interesting work. Compliments.
Any questions, if anyone?
I think we had a lot of questions.
Yeah.
Which question would you ask to yourself?
That's a very tough question.
But I still think if you return back to your figure with how it calls the phonons, yeah, this one, right? So it looks like, yeah, we see the difference, and we definitely see the difference between initial and the final, or kind of like we can make this analysis. But again, we probably need either normal mode calculation to know the frequency of real normal modes, right? Or really go beyond, like, kind of try at least what Levi was suggesting, to try metals, non-metals as nearest neighbors, right? So we will see more information, what exactly contributed which frequencies and which this coupling, like, for example, you have coupling at 200, right? For the bottom one, which is what, both HOMA and LUMA, the low state coupled to this 200 kind of frequency mode. So what exactly this mode? And yeah, it's in a range of optical mode, right? But is it, looks like it cannot come from the chlorine.
So I thought
because your HOMA LUMA not
it's from the
really.
lead, maybe, because I consider this a lead chloride one.
Yeah, but this is becoming very confusing because looking on your black and red on that side looks like, oh, at 200 we have really only lead. What is your black? Lead chlorine or whatever. On the right side, the black line corresponds to lead chloride. But we know that HOMA LUMA not associated with fluorides, right? So electronic levels.
Another thing is, I think is because I consider only one pair, so it just if each picture can give us a lateral optical phone, it won't give us any information about transverse phone or what's it called?
Azimuth, right? I understand. That's why I said, like, it's not really giving us a full information, and at least if you include these metals and non-metals to calculations of your right plot, right? So maybe we will see deeper ideas how to connect this. Would be perfect to get. Oh, by the way, about normal modes, especially as we did you have a time to discuss with Dayan?
Yeah, I sent him this stuff.
So since they calculate dynamics, they really need to calculate normal modes, right? So any of you, because we were putting these questions all the time to Levi and I guess to you as well, and I think, we don't have Erin here, right? But maybe Loon, have you done any calculations on normal modes? No one of Dmitri's group were doing normal modes?
I've computed normal modes, but not for the systems that we're
But for core shell?
No, because it takes much time.
The question is, how is it doable?
So,
I mean, it takes much time, but the question is, can we do it? Is it doable?
It is.
Okay,
so
good.
There's a program that I learned about this when I was at Los Alamos classes. Yeah, it's atomic simulation environment, and it's a puppet master of VASP, so it gives VASP geometries, but it doesn't run as VASP does, where it does 6n plus 1 calculations at a time. It does like a single point, and it just gives geometries. So it can save all the data. So if something happens, you can restart it without having to recompute all
Mhm.
of the geometry.
But you know how to use it, right?
I don't.
So you,
Braden is
knows
learning.
it.
Braden is learning.
Yeah.
Now maybe you guys also should learn it. And try at least to get normal mode calculations for your systems. For core shell and for the nanoplate.
Yeah, I
And
have
for
one
nanoplates,
question
it probably
in
would be
this
much
case,
easier to get because you have periodic boundary conditions, much less vacuum. Your periodic your calculation cell is smaller actually than the core shell, right? Although the size of the structure is pretty much the same, 16, 68 atoms, right? So, and if you have the normal modes, we easily can then align this pop out guys with real phonon spectra and see, oh, this is this mode, and this is that mode. Although, maybe not very much. Because again, then you need to look on the displacement to figure out what exactly the motion is involved, right? Like the phonon modes, the frequencies, right, will not tell you what exactly the mode is. So you need really to visualize this motion, right, to see the displacement. And then you say, oh, it's LED, or LED, or whatever, or stretching, or bending, or whatever, right? So, but yeah, I think at least this approach with putting more atoms, like really find the distance and changing the distance between all atoms in your system rather than just those which supposed to make the bond, right? Probably will give us also a little bit more depth.
Did you ever look at if state crossing is important for your homo-lumo gap?
State crossing is, in case of homo, in front orbital, they don't.
Can you go to your very first or second slide where you're showing change in energies? Yeah, this one. So
front orbital is pretty much same, I guess. Yeah.
I would have.
Yeah, there are one few, I guess, in the very about 2.67 picosecond time.
2.67.
6 or 7, about that range. On the unoccupied orbital.
It looks like you do have at least one crossing on your LUMO.
Yeah, I see.
Yeah, there's
one
another
here.
one
So that could also be. It might influence it, so you get peaks at where you shouldn't get peaks, right?
you mean for frequencies?
Yeah.
But for frequency, we don't have any idea.
But
why
the thing,
should we
no,
choose
it's probably
that?
should not have, because again, don't forget it's a semiconductor, right? So means all the states near, like it's not just Luma. It's Luma plus 1, Luma plus 2, and so on. They're all pretty much the same kind of degenerate, nearly degenerate band with pretty much the same character. So that's why even if they kind of cross or flip, their character is probably changed
But
insignificantly.
That
It's not like in a molecule, then you have orbital localized on this side of the molecule, and then you have an orbital localized on completely different side of the molecule.
I'm not saying that
Right?
it does not. I would agree that the non-adiabatic dynamics, it has small effects, but if you do the FFT of it, it only cares about energy and how the energy is changing. So if you get every 100 femtoseconds, the energy crosses, that could show up in your FFT.
Yeah, well,
But why you think
that
it's
can
not?
introduce that
Why you
some
think it's wrong?
Because
It's if they cross, it means it's really very strong coupling. So it's they really coupled to some mode. Yeah. So
But then to
they're not
say-
completely off of the picture.
then to say we don't suspect that it in the FFT of interatomic distances, right,
Yeah.
there might be a point where there's no
They will not
spectral density,
correlate. Yes.
and then you could say we suspect this is due to we're in an adiabatic basis, so states are not ordered, so we get some frequencies that pop up randomly because of that. If going to all pairs of atoms does not show anything strongly at 200.
But again, this kind of crossing is probably not happening periodically. That's another thing, right? So which means again, this will be not really affecting very much the Fourier transform. If you really see it periodically appearing at each 2 femtosecond or how many, then of course you're right. But again, I don't know. But it's a good point, yeah. And again, this would be very, very important, as we saw, if you remember, of course, in summertime when it was discussions on the stuff which left from Pang and Fogel, John was discussing this kind of story. So when we have in a charge transfer state, ligand molecule versus a quantum dot, right? So kind of this crossing really was completely changing the character of the orbital, and then we get in completely wrong result just because we thinking it's the same, but it's kind of not the same orbital anymore.
It inflates the rate at which it decays because it can jump states faster than it should.
Yeah, and in our case it was even worse because the gap was close, so it's really kind of jumping between homoluma with completely different nature of orbitals, and then of course we not were able to get any physical information from our simulations, which he ran for a couple of months, and at the end we got almost nothing from it.
But our system, we got a...
Yeah, but when gap is open and kind of...
no, our means that die quantum was then working. That's similar to the John.
But gap is open in your case, right? So it should not be this issue. Because in his case,
our system is
the orbital of the die was so close to the occupied orbital of the or unoccupied orbital of the die was so close to the unoccupied orbital of the quantum dot. So you kind of close, like it's like this, but it's really very close. So you kind of artificially close the gap and make it metallic instead of semiconducting material. And yeah, and then it was.
But we got some. We did have some wrong charges in our system. Then we got it.
But you fixed it, right? Yeah, it's
something
exactly
like
what
that?
John was checking. It looks like in that case, which Pan was working on with a different, because you work on a different die. He was working on, I forgot whatever he was working on.
Something that dies.
So the die was really kind of make all this gap closed, and independent on the charge, we didn't get any better opening, any better picture. Yeah, but for this system, I guess this is probably not so critical.
Yeah, this one is pretty. We have a sub gap in the orbital too, so we need to do that. Okay. So, anyone
Done?
have any?
Good. So then I think we have no any other presentations, or maybe
For today.
For today, yes, for today. Or maybe someone wants to. No? No volunteers? Then yeah, have a nice weekend. You're free to go wherever you are going to. Maybe back to work.
Very encouraging.